This highly accurate 3D model demonstrates the critical contact point between the wheel and the track.
This 3D model shows a neutral metallic wheel set. The cross-section clearly highlights the importance of the conical taper.
3D model, we observe the wheel flange, the primary safety guide, slowly detaching from the main body of the train wheel. Of self-steering, where the wheels navigate the curve smoothly without external guidance.
This highly detailed 3D model emphasizes the structure of the track. Focusing on the inner and outer rails, we see the
enters the curve. Observe the gentle, controlled lateral shift, which maintains stability, causing the wheel set to move towards the outer rail, focusing specifically on the interaction at the flange. This slow-motion demonstration, notice how the outer wheel rides on its larger diameter, while the inner wheel simultaneously
model, we see the critical wheel-to-rail contact points. The bright green indicators highlight the larger radius on the outer wheel.
As the train navigates the curve, notice the critical contact points. The bright red indicators highlight the smaller radius. Curve is the difference in distance. The outer wheel must travel further than the inner, a problem solved by the wheel's tapered design. Allows for a difference in rolling distance, which acts as the steering mechanism, guiding the train precisely along the curve. This cross-section highlights the precise engineering of the conical wheel. Observe the consistent contact maintained. As we approach this curve, the super elevation, or banking, becomes clear. The outer rail is raised significantly. This section demonstrates super elevation, or track banking. As the train enters the curve, the banking reduces. Banking the track, engineers utilize gravity to create the centripetal force required for safe turning. Highlights the synergy between the wheel taper and the banked super elevation, allowing the train to smoothly navigate the curve. The train moves, the wheel flange maintains a precise, consistent gap from the railhead, ensuring smooth operation.
Against this overly sharp curve, the flange gently touches the rail, demonstrating its role as a crucial safety backup guide.
Highlights the wheel set mechanism. The parts move out, emphasizing the rigid axle connecting the two wheels before moving back in. A cross-section of the wheel rail geometry. We zoom in on the slight angle of the railhead itself, complementary to the wheel taper. It's the stability of the mechanism. It naturally seeks a central, stable path, known as self-centering.
We compare straight versus curved track geometry. Notice the uniformity of the straight section, while the curve requires precise.
This close-up animation demonstrates the lateral shift, or hunting motion, that initiates conical steering.
Engaging the curve, the red and yellow gradient highlights the significant friction and potential wear concentrated at the flange-to-rail interface. Cross-section, the blue area highlights the ballast, the critical support structure that ensures the stability of the rail system.
Differential diameters engage due to the conical design. A steering force is generated. This force clearly illustrate how the outer wheel covers more distance than the inner wheel, thanks to the subtle lateral shift on the conical tread.
Highlights the conical wheel taper. This mechanism allows the wheel set to self-center, ensuring smooth travel along the track.
Here we see a detailed 3D model of a track section. Notice the super elevation, the precise vertical distance. Here we see the wheel set engaging the curve. The conical design ensures that the outer and inner wheels rotate smoothly.
The simulation highlights the expansion of the outer wheel diameter.
Highlights the flange, seen in purple, demonstrating its vital safety role in keeping the wheel securely on the rail. Curve setup. Notice how the gray block model moves smoothly around the bend, demonstrating the system's effectiveness. The entire wheel set track assembly. The components, including the wheels, axle, and rails, move gently apart to show their separate roles. Cross-section shows the center of gravity relative to the banked track. The banking, or super elevation,
produces an inward force that counteracts the outward centrifugal force, allowing the train to navigate the curve smoothly at high speed.
Focusing on the wheel set behavior. As the animation repeats slowly, observe the lateral shift of the assembly on the track. Inward ripple effect from the contact point, resulting in a controlled decrease of the inner wheel diameter. Shifts too far, the taper naturally corrects it. This cross-section highlights the critical interaction point. The red area on the wheel tread demonstrates where the maximum turning on the wheel flange. This simulation demonstrates safe, minimal contact with the rail. Although less than ideal,
Rail fasteners. The clips and plates provide the rigidity needed for the track's superelevation, allowing for the safe banking of the train.
Conical shape of the wheels, the train's bogie functions as a self-steering differential system, ensuring smooth navigation through curves. The wheels allows the inner wheel, where the blue highlights the contact point, to effectively shorten its rolling radius on the tight curve. Conical profile allows the outer wheel to ride on a significantly higher circumference, shown here in green. Cross-section highlights the standard wheel taper. The crucial measurement is a ratio of 1:20, or 2.
Slow motion. The wheel set resists the turn, forcing the flange into contact with the inner rail before the conical profile takes effect.
We see the crucial point of contact. The red and yellow highlights precisely visualize the friction and energy loss that occurs. Superelevation, or banking, is crucial for high-speed rail. As the train enters the curve, the track tilt
Reveals the precision components of the wheel set. Watch as they are seamlessly pressed together, forming a single, rigid assembly.
enters the banked curve. The vertical alignment of the track counteracts the centrifugal force, ensuring stability and smooth passage.
The diagram illustrates the resulting net force vector, clearly pointing towards the center of the curve as the train navigates the bend.
Stability of the rail network relies on the ballast. These crushed gray and black stones lock together, preventing.
A wheel set is comprised of two wheels rigidly connected by a solid axle. This design ensures that the banked curve, the centrifugal force is counteracted, shifting the weight distribution slightly towards the inner wheel.
The flange, highlighted here, is essential for safety. It maintains the wheel's position on the track.
Track view highlights the gradual transition from the straightaway into the curve, showcasing precision engineering. Energy transforming. The vibrant red and yellow demonstrate the intense friction as the wheel flange presses against the outer rail. This 3D cross-section illustrates the interaction between the wheel and the rail. The height difference, labeled H, As the wheel set approaches the curve, you can see how the gentle steering mechanism guides the train precisely along the track.
Scenario. A wheel set on a curve with no banking. This instability leads to significant flange contact and excessive wear.
Wheel set turning angle being proportional to the lateral shift on the track. Vast distances lies in the wheel's large diameter, maximizing the distance traveled with every turn.
The train effortlessly carves through the lush landscape, showcasing the seamless integration of modern engineering and nature.
Movement shows the wheel set settling precisely into its stable, centered position on the track. This highly detailed 3D visualization demonstrates the critical wheel-to-rail interface. Highlights the conical taper connection. The wheel gently slides out, then returns, demonstrating the precision engineering of the assembly.
This detailed 3D visualization highlights the interaction between the wheel set and the curved track. A closer look reveals rotates. The blue overlay shows the ideal contact line at the mid-taper, demonstrating perfect interaction with the rail.
Inner wheel rotates slower, while the outer wheel accelerates, demonstrating the differential gearing within the clock mechanism.
Here we see a detailed visualization of the conical wheels. This specific wheel taper allows the train to self-steer around bends. We see the wheel set perfectly centered. This configuration, with equal rolling diameters, ensures optimal. As we zoom closer, the technical detail of the rail profile becomes clear. This cross-section is crucial for innovative design of the bogie, or truck assembly. These components are essential for holding the wheel set securely in place. Observe the friction visualization as the wheel set enters the curve. The vibrant red and yellow demonstrate the localized. First, the taper, the conical shape of the wheels. Next, the shift, lateral movement of the wheel set. As the track straightens, churning up lobslides. Highlights the flange, which serves as the ultimate backup safety guide. Notice the gentle, controlled touch before the release. Visualization demonstrates the self-steering differential principle. Notice how the conical profile allows the wheels